Hi, my name is Dennis. Welcome to Foundations Networking, Routing, and Switching. Let's get started. Our learning objectives today include understanding the relationships between frames and packets. We want to identify routing protocols and how routing actually works deep down. And we want to be able to understand how to forward traffic between two networks hands on with our tool sets and analysis skills, and how to actually frame everything around OSI layer modeling. So, first, let's get a quick review of frames versus packets. Remember that frame starts at layer 2, packets start at layer 3. So our encapsulation concepts, again, still hold true. The packet doesn't get created until layer 3, which we'll find right here. So remember that layer 3, and this is layer 3, you have an IP header and you have data. Nothing is read until the next layer. Remember that we have the premise of a 7-layer OSI model. Can you guess where layer 2 is? Oh yeah, that's right. It's down here in the link layer, data link, right? And that's where a frame is, where it has MAC addresses and things of that nature. We also have what we call ARP, helper protocols. So address resolution protocol, and it helps link layers 2 and layer 3 together from a mapping perspective. ARP specifically does this. It says, hey, I know of an IP, but do you know the MAC address? Right? What is the MAC address associated with an IP address? Reverse ARP says, I know a MAC address, but I don't know the IP address. Can you help me find that? That's the whole point. And ARP actually utilizes that protocol linkage together, and you use it every day, such as your homegrown network, on the network switch, and other items that are of interest to help you get an IP address and help your local network map IP addresses to their local destination MAC addresses. MAC stands for Media Access Control, and remember that MAC always has a frame. Remember that we also have the concept of encapsulation. So let's erase what we have here. Last part here. And then also, as we go up, we're actually encapsulating additional data. So a frame includes everything in it, which includes potentially a header and other payload information, but it doesn't know that there's an IP header, and it doesn't know that there's a UDP header. All it knows is that if there's not a MAC address and frame related to that frame header, then everything else is just data. Same thing with IP header. We have IP address, source, and destination, the options is accordingly, and everything else is just data. It doesn't have an understanding of a UDP. UDP being another header, which is a fixed 8-byte item, and we have UDP data, and of course the application at the very top is the only one who understands that, such as DNS. So Ethernet frames are at layer 2 concepts, right? They are layer 2 concepts yet again, and again they have MAC addresses. You have a destination MAC and a source MAC address along with the Ethernet type. Everything else that follows is considered the trailer portion of the payload. Of course, there's also a footer, which is sometimes called a trailer, which has a seriously checksum, which is a fixed 4 bytes. So your Ethernet frame typically runs as small as 64 bytes to 1518, but most of the time, most MTUs or maximum transition units max out around 1500 bytes. That's how we measure things in most cases in the networking world. So we talked a little bit more about address resolution protocol, ARP. Right, just give you a demonstration of what that really means and how it maps together. Let's look at the concepts. Right, ARP is the glue protocol to the IP and MAC address mappings. Right, it allows layer 3 IP address translation to a MAC address on your physical local network. Right, and it's an abstraction at your switch. So what happens is your switch actually has tables. Right, it has mappings of tables between IP addresses and MAC addresses. So, for instance, if these 3 switches are connected together over an uplink, we have host that's 10.0.0.11 right here with a certain MAC address, and it needs to know who's at 12. Well, it goes to this switch and says, who is it? And it'll send a broadcast information out to all Fs. That all Fs means that there's a broadcast message going to who knows about the IP address 12. The switch or other host might respond with a gratuitous ARP if required. So gratuitous ARP just basically means it's also providing answers so it can actually help the switch and other hosts fill up the cache table. Non-gratuitous ARP really means that the switch or someone else specifically replies saying, I'm .12, here is my MAC address. In this case, my MAC address is whatever, right? my MAC address would be here at 12. The same thing happens to other switches and across between, if you have linkage between these different switches, those broadcasts go between these different switches because everything that you uplink to these switches are at layer 2. There is no routing, there is no packet. All it knows is that there's some sort of other IP address associated with these hardware MAC addresses that the switch actually knows. Okay, let's get into concepts of packets as part of our review as well. Packets, remember, are at layer 3. You have to keep that in mind. So when we say we have a packet, that means you have an IP header. Our IP header looks something like this. Now, there's a lot to look at right here, but focus with me here. The main key fields that we are focused on as far as beginner networking, we're looking at TTL, which is time to live values. How long can that packet stay on the network before it needs to be dropped off by the protocol standard? What's my next protocol in the upcoming header? What am I encapsulating? So IP header, I did say that each layer doesn't have an understanding of each other layer. Well, that's mostly true, but remember that the protocol is the next header layer information that routers and switches can actually process things and firewalls as well. For instance, if you have an IP protocol ID number behind of 6, that means TCP, right? If I have a 6 right here, that means TCP, actually I'll put it right here so you can see it better. That means TCP is actually coming behind the IP header. And so forth, we have the same values over here. They're just values or information. Let's erase all that. Now let's go into the next one, which is source and destination IP addresses. So these are 32 bits wide, aka 4 bytes long each. And that's because why? 2 to the what? 2 to the 32 gives you your total amount of IP address spaces within IPv4. So just think of 4 bytes wide whenever you think of the 4 here. And if you don't know how to count the bytes here, you go right here. There's the offsets and the number of bytes. These key fields are pretty important for understanding the routing and switching portion of our lecture here. Remember that protocols are just whatever's coming after. Your TTL is your time to live. So typically Windows might have a starting TTL of 128. Linux and other distributions might have, and even Mac addresses, or Mac OS X, not Mac addresses, will have a TTL of about 64. And sometimes some devices start with a TTL of 255. The maximum allocation value that you can have is 255 as a whole. Now, there are many other flags here and options that you can keep in mind here, but at a minimum, your IPv4 header always takes 20 bytes, right? It always takes 20 bytes, assuming that you don't have IP options in here. That can become variable and can grow to a larger portion, but that's typically the modern network space. So what do you do with these IP headers? Well, you have a concept of trace route, right? These increment a TTL value from 0 to 1, 1 to 2, 2 to 3, and 3 to 4 accordingly until it hits the next router and the routing path. When it dies out, it maps the router from the last ping or last hit, and then gives you a mapping of latency as well as where it took the path for the header. Over here, I have a path of 3 routers, so I have TTL version 1, TTL value of 1, 2, 3, and 4, so it reaches my final destination, which means at TTL 4, I have 3 routers in my path, but it took 4 hops total before it got to the destination. Each hop is a router, and it can be traced by multiple protocols. So you don't have to be relying only on layer 3 ICMP. You can also have TCP or UDP. The main difference is you have to have the ports open to get that validation. Otherwise, you have to have ping enabled, ping being ICMP echo and replies to actually get that information, including the latency measurements between. Okay, the importance of routers. So routers, remember, are at layer 3 and above. And so what happens is you'll actually have a router for each different forwarding between networks. So if I start off with 192.168.1.0/24, I'm on this network segment leg. And then remember, routers, to actually move between networks, you have to be physically connected to another network. If there's a peering network of 192.168.12.0/24 that these two routers are connected to, let's say they're inside a building for the same enterprise. And then it's also connected to a disparate network of 192.168.2.0/24. That is really 1, 2, and 3 networks together. 1, 2, 3. And we have 2 routers, but we have a shared linkage between network 2. Okay. You can utilize things called network address translation, which we'll learn about in a different module, but it requires an understanding of different networks and making forwarding decisions based on the different networks. So if nothing is inside 192.168.0.1.0/24, which is in network 1, it must be forwarded over to the next routers known in the route tables for 192.168.2.0/24. What does that mean to you? Well, routing tables look a little bit differently, but we'll showcase those in a second. Let's get to what I just said earlier, which was, what is network address translation? What is NAT? I mean, NAT. So NAT, network address translation, comes in really a very simple format. It was really to delay the exhaustion of public-facing IP addresses. Now, you might not know this, might be a little younger than me, but we had the concept of every host had to have a public IP address because that's how you route across the internet. Yet everyone has to have an IP address. So you have a concept of private IP addresses instead. So to do this, NAT basically said, hey, instead of having everyone with 150.150.0.1.2.3.4.5 with every host on my network, maybe just give me one IP address instead, and let me have an internal IP address scheme called NATing. We call this RFC 1918s. And those are actually the standard and specification for the 10.0 networks, the 192.168 networks, everything else that goes in between. Basically what happens, just like with ARP, NAT is a helper protocol. So it basically translates a public IP address to one or more private IP addresses. So on your local network, you may have 192.168.0.0/24. But you might be on the external side using a single IP address, and that helps us conserve our actual public-facing IP addresses for other routes and very specific needs. It also acts as a somewhat of a security mechanism, but not entirely. It wasn't the original intention, at least. Okay, we also have routing protocols. So routing protocols operate in a couple of different ways. We have static routes, which we basically say anything that is not in 192.168.0/24, for instance, you stay local, right? That's my local network. If there's anything in 10.10.0.0/24, maybe you go to another network router, which is at sending in 10.10.0.1, and anything that is not in between all those, and we call those the gateway of last resort. That goes out to another gateway, which is perhaps 10.10.0.1 instead. Understanding that this is a route table example, and so understanding those routing protocols are basically saying I'm either updating the route tables manually, which is what I just did now, or the routers are smart enough using a routing protocol, dynamically updating it either for interior purposes, for inside network, which is RFC 1918 again, which is those 192.168 items, 10.0.0/8s, and 172.16/12s. Let me erase all that here. There we go. Get that last bit. Okay. So basically, routing protocols are exactly what I just created, which is a static route table, but they update themselves. So again, they're layer 3. And so they can say, well, if I kill a router here, I need to update the tables so that routers 1 here and here know about them accordingly, and I can draw a different path out from PC1 to PC2. That's all routing protocols really do. And so, but there's security impacts related to them, such as who controls them? Do you have authentication? How do you have a mutual secret? And what if I injected myself as a wannabe router, as a PC, maliciously onto the network and say, hey, update your routing tables? That would be pretty bad. So routing tables also have a built-in concept of authentication. But remember that routing tables can either work dynamically or static based on what I just did. Dynamic exterior, which is focused around public-facing IP addresses. Dynamic interior, focused on what? RFC 1918s, right? Your 192.168s, your 10s, your 172s. Okay, let's get a quick demonstration of our dynamic routing tables, or actually static routing tables in this case. Okay, so I talked a little bit more about what a static routing table looks like. If you actually go into your command line And if I can get back into my system here, oh, that's the wrong one. Let me click on that here. Go back, put my pen back. There we go. So we have route print right here, which you can run inside Windows. There's also just route that you can run inside Linux. And really, what you have is a routing table that's generated for you by the system, but you can also statically create these yourselves. Notice that I have multiple networks here with the destination intention. And of course, I have my gateway information right here about each different network. Generically speaking, the lower the metric, the higher the priority in most cases. And of course, I have my interface information up here, which says, hey, which interface means what symbolically inside the operating system. That's all it really means. So if there's something coming out of 192.168.0.0/16, it's not in this routing table, it's going to go to the gateway of last resort, which is go to the internet somewhere. Next, we have dynamic interior routing. Right? Protocol examples include IGRP or EIGRP, which is enhanced version of IGRP. IGRP stands for Interior Gateway Routing Protocol. And so you can actually mix and match different interior routing protocols as long as they're compatible with each other. So we have 3 different networks with 3 different types of RC 1918 addresses, which I talked about. The 10s, 172s, the 192, 168s. If you configure the same compatible routing protocols with each other and say, I have an autonomous network, I have a network cluster grouping of these routers, and these are routers that belong to me. 2446 in this case is on one side, and I'm going to connect to items on the other side. You just make them aware of each other, and then bam, you have dynamic interior routing. Now, there's many other concepts of tuning and performance and security around these, but this is the very basic way you can actually enable dynamic routing protocols on your network, and it updates these tables accordingly for you instead of you doing it yourself. These are actually command line syntaxes from a Cisco router between them, and that's as simple as it is. You either enable them or you don't, and they update each other based on mutual authentications, such as strings or an MD5 hash, and in some cases, better authentication mechanisms. You have dynamic exterior routing, which has the same premise. So regardless of what you try to do, they are focused on edge routers, right? Public IP addresses. So if I wanted to go ahead and route between Google and DigitalOcean, which are 2 cloud providers, I need to have a BGP ping session instead. BGP stands for Border Gateway Protocol. And then in an upcoming demo, we'll see how routes actually interact and how you can configure them inside your actual network, or at least a virtual network that you can install on your own systems to play around with. Now, that was a lot of information, and you saw a lot of different things about headers, packets, and frames. Let's look into a demonstration about how we can actually mobilize it and utilize actual packets and information. Go ahead and take a break and return back and resume the video based on what you're looking for. And we'll get to our lab and our demonstration in a second. Hi, and welcome back. Hope you had a great break. Let's look a little bit deeper into traceroute, at least for Windows traceroute, using ICMP. Now, if you're using Linux, by default, it utilizes UDP. You can change that to TCP or ICMP based on your settings. Look at the manual page as accordingly for your OS. So we're going to open up Wireshark in this case, and I want to demonstrate to you what actual ARP looks like on the network. So if I actually open up my command line window here, I'll type in ARP-A. You can do the same thing on your Windows and Linux machines, as well as Mac. And you notice that I have a MAC address mapping list all the way to my IP address as seen here. Now, how does that get generated and created based on the caching of my local host here? Well, that is based on information related to gratuitous ARP or ARP replies directly to me. Let me pick one. This one looks pretty busy. I'll create a capture filter of ARP. And here we have our different whois and responses as a broadcast information, of course, to my network. So broadcast information, who is coming from who. We have potentially my ubiquity switches, and it's telling each other, hey, here's my reply. Now notice that I don't have gratuitous ARP So some network switches and devices may have gratuitous ARP, which will be labeled as GARP. And then so it might give replies without actually being a request for that. So if you see a lot of gratuitous ARP on the network actually coming from like a Linux host or a Windows host, that's probably a sign that you might have an attacker on the network sometimes. Now we see a sender MAC address, IP address, target MAC address, and target IP address inside each of these replies, as well as the request accordingly. So who has what? Remember that the target MAC address is always zeroed out in the actual item and saying who has the MAC address towards 20.1, for instance. Right? Who has the MAC address for whatever it needs to be. So here's our broadcast information, and here we're just capturing based on this broadcast information here. Who has 20.1, tell 20.198, and that could be someone coming onto the network. Now, because I start seeing this more and more often, and it's coming to tell 20.198, it could be a couple of things. And it could be a couple of things because maybe I can't grab an IP address on the network for whatever reason, and it's coming from the same people. Why does it keep broadcasting this? Well, maybe it's because it's not listening for a response, or perhaps it has a DHCP reservation or a IP static manually configured address that isn't providing responses anymore. So those could be signs of issues on your network, depending on how often and how much it floods. Network devices and different operating systems work in weird ways sometimes, so you might not see everything that you're looking for, especially if it's capturing on a network interface that is virtualized, or if you have other information in here. So I just wanted to give you that notation of what that might look like. Let's go ahead and close this capture. Now let's capture ICMP because that's what Windows uses. Utilize the correct layer 4 protocol if you're using Linux for your testing here. So ICMP here, we're going to start pinging some. So here's a ping echo request. So if I ping google.com, it's going to ping 3 times by default, at least with this one. And it's going to give me a reply for each one. So it looks like I have 1, 2, 3, 4 instead of 3. So 4 sent, 4 received. Perfect. And this is what it looks like. It has payload information that is understood at the ping layer. But really at the ICMP layer, I only have a type 8 and a code for echo request and responses. So type 8, it's ping request. Code is 0 because it's a request. But here's my reply. Type 0 as a ping reply, code of 0. All right, so let's see what a traceroute looks like instead. So let's go ahead and clear this real quickly. We still have the same capture filter. We're going to do a traceroute. And we're going to say our maximum hop count should be 10. And we'll still go to google.com. Now we start seeing the TTL incrementations, time to live, exceed it. And I'm still getting responses because ICMP is indeed allowed because we saw the items here. Now we'll see where our backbones are going. What kind of ISP information might show up here? I have Comcast and I'm in the Houston, Texas area. And we look at here, let's look at the ping request with the TTL. Let's go into our IP header here. Sequence number, other information. Right, we have our time to live already exceeded here. Yep, here we go. Time to live exceeded information here in transit. And that's ICMP information to help you with that item. Let's close all that. Let's look at the IP header. So our ping request here, we're in IP version 4 header. Let's look at the protocol information and dig down. Time to live of 1. And we have an ICMP saying, hey, it exceeded. Here's my information here. Now we have a time to live of 1 here. We should see that increment. Yep, time to live of 2. And so forth. Sometimes we see ICMP port unreachable, saying that we have a blockage of ICMP going out. And here's my response information. So we have a bunch of data here that doesn't necessarily mean anything to a lot of people, but it means something to computers. So we did succeed in our trace completion to Google, and it looks like I used some sort of point of presence, so it doesn't actually go across to San Francisco. It's hitting some sort of like data center closer to the Texas general area, backbone, Comcast Commons. Okay, well, very cool. And so we go down here for time to live. We should start seeing information related to not the ICMP, but we actually want to take a look at the IP header, and our max time to live value of 10 matches our maximum request here. So that's all it is. We're just using ICMP to trace where you're going through. So I had no idea that Google, if I go to google.com, I'm still going to go only in the Texas background here. Actually, I did have a little idea, but let's say you might be surprised that a data center may not be anywhere near your state. You can actually trace where it's actually going and where it thinks the routing paths are most optimized, and you can actually help understand if there's latency between the average of 3 different ping requests at a time. Okay. Now let's look a little bit more about how routing tables operate. So we looked at terminals and terminal routing tables for static analysis. So if I go to route print, I see information about routing information here. So I should use the gateway of 192.168.20.0 or 20.1 in my case, but anything that's not going to any of these networks right here. And you're wondering what these are called multicast. So you see 224 to 240 multicast addresses and network information. You as a person at home is probably never going to see this. And of course, we have broadcast information right here on the same link. Okay, that's pretty cool. How do we actually get from router A to router B to router C on these different adjacent networks? We have 192.168.1.0/24 here, and the same linkage, and then we have 2.0/24 instead. Okay, well let's go ahead and configure our routers, and this is a program called Packet Tracer. We'll simulate that we have 3 different routers on 2 different networks connected to each other, and we'll pass through router 1, router 0 to 1, and then router 2 accordingly here. Now you'll do this in your lab, but I want to show you some interesting information and how you might be able to do it in real life when you're plugging these up. You can look at the front and the back of these physically if you really want to and see how it looks like in real life. We're going to the CLI directly. This is what you'll do when you go into the console as if you were to boot up into the actual router itself. So we have router information that's booted up. I'm going to enable configuration mode. I can go press question mark and see what it's available to me. This allows me to do administrative related functions as well as do trace routing and other information. I'm going to use config T, which is configure terminal mode. You can actually type it all out, tab it out correctly. You type an exit, go back to your breadcrumb here, and you see a little hashtag accordingly. Config terminal, which you can use auto tabbing, does the same thing. All right, so we're going to configure our interface. We'll say interface tab out fast Ethernet 0/0, which is the this stands for module 0 port 0, so the very far left top. All right, I'm going to configure that port, and I'm going to say IP address, and we're going to give it an IP address of 192.168.1.1 across this subnet /24. And we'll say no shutdown, basically saying turn on the port. Now it's saying the link is up. I should start seeing green to this later on. Now let's do the same for router 1. Enable config T, and then IP address. Interface fast Ethernet 0/0, and the IP address of 192.168.1.2, because it's the same segment, we can't have the same IP address. And then no shut. Now it's up. Now you see the green link light equivalent right here in our virtualized network. That's pretty cool. Let's configure the next port. So we want to make sure that router 1 has connectivity to the second segment of the switch. So we'll do this. We'll exit out here. And we'll interface fast Ethernet 0/1, which is the next port over virtually. And we'll say IP address 2.1 because it's on this segment instead, physically connected. All right, so that's our /24, and we'll do a no shut. Just turn that link on. Let's go to router 2. Make sure this turns green so we have our layer 1 and layer 2 connected properly. You can also look at the different commands here if you want to look at the route tables with little breadcrumb hints. Enable conft interface fast 0/0, and then we're going to say IP address 2.2. Now we have a green link light. Now, at this point, can I route between any of them? The answer is no, because we have layer 2. We don't necessarily have anything else going for us. All right, so now we need to create the actual routes on the route table. This is static route creation. So let's go back to router 0 so we can understand what our routes look like. All right, we're still in the interface configuration. Let's go to config mode only, and then we're going to configure our IP route, a static route instead of dynamic routing of 192.168.2.0. Right, anything going to 2.0 needs to understand which router is next in the list, which is 1.2 in this case. So we'll say IP route 192.168.2.0/24. Go to router 1. Cool. Now let's go to router 2 and do the exact same thing going in the reverse. You always have to have a return route. So we'll do IP route 192.168.1.0, right? Returning to 1.0. And then we're going to say, hey, this is my next hop router right here, 2.1 interface. Okay. So I should be able to ping 192.168.1.1 if my routes are good. Oh, and I have to ping it from the enable mode, not the config mode. So I'll do ping 192.168.1.1, which is router 0 here. And let's see what's going on. We have a 60% success rate. So it means that depending on your CPU utilization, how reliable your internal network traffic is, this virtualization may have different aspects. So you might see 80% or 100% rate. I'm using a lot of CPU utilization right now, so you might see not 100%. But it is up, and we have a success because 3 of 5 packets made it and back. So let's go ahead and figure out why this works. So you can also save the config information. But let's look at a show running config, and you can see everything that's been configured so far. Unfortunately, it does show your route information here, but you can also say show route. My apologies. Show route. Interesting. Let's try router 1. Maybe it's because we needed to save it. It's because we probably need to save it. So we'll write it to memory, show route, and it's still saying that we don't have it. So what are we going to do here? Well, we need to actually do IP route instead. And we're going to do a show IP route. There we go. So gateway of last resort is 1. Directly connected. So we have 1.0/24 connected to here. And 2.0 needs to go via 192.168.1.2, which is my network segment leg right here. All right, so let's look at here what I need. Instead of show route, I need a show IP route, and then I need to make sure I've written my configuration to memory. All right, so let's do the same thing here. write mem, which is the same as write memory if you tab it out. And then we'll do a show IP route instead. And I get the exact reverse accordingly going. See that S right here? That's S stands for static, and C is the cable connection directly to that. So you get your codes right here, and you can see where you have dynamic and static routes accordingly. Now, if I configured IGRP, RIP, or something like that, this would have been relatively easy. But if you imagine if you get to 5, 6, 7, 500 networks, what will you do? Well, dynamic routing makes a little bit more sense instead of using static routes all the time. So I hope that gives you a little bit more clarity into routes and how we can actually use routing tables and what they might look like when you actually connect them to different routes, or what the configurations might look like in your routing tables, and then ultimately what they mean. We'll see you in the next module, hopefully, and have a great rest of your day.